Hello, and I would like to perform a calculation as it relates to electric current, and I would like to show this problem in order to find an electron drift speed. So let's look at this following problem. Electron drift speed of 12 gauge copper wire. Now, 12 gauge copper wire, it turns out as the wire gets thicker, the gauge of the wire actually gets smaller. So this is a certain rating. It's 12 gauge copper wire. And the mass density of copper is rho. So that's the mass density, okay, is equal to 8.95 grams per centimeter cubed. And it has a cross-sectional area of 3.31 times 10 to the minus 6 meters squared. Suppose this wire carries 10 amperes of current. So that's the electric current I is 10.0 amperes. And we want to know what is the drift speed of the electrons. So what's the drift speed? And we're going to assume one free electron per atom. Okay, so notice that in order to relate the drift speed to the electric current, let's write down the equation. And the equation looks something like this. Electric current times number electron density per atom, so that's this N, I'll come back to that, times the magnitude of the electric charges times the drift speed times the cross-sectional area. So the units of this are number per meter cubed times charge in coulombs times meters per second times meters squared. That all comes out to units of coulombs per second in SI units, which are amperes. Now, notice we know what this value is. If we are looking at the magnitude of the charge on an electron, we know that to be the so-called fundamental charge. That's about 1.60 times 10 to the minus 19th coulombs. That's a well-known number from experiments. So the cross-sectional area is actually this, 3.31 times 10 to the minus 6th. So notice the drift velocity can be found as long as we find the number of conduction, the number density of the conduction electrons. So what do we mean by that? Well, this has units, as I stated, of number per meter cubed. That's the SI unit. Okay? But let's go actually perform a unit analysis to see how we might actually get there to number per meter cubed. Well, first of all, we have mass density in grams per centimeter cubed. Notice that that should be converted, so that we have to convert centimeters cubed in the numerator to meters cubed in the denominator. So we'll get to that. Then notice that grams is mass. We need to get that to number. In order to get that to number, I think we have to use moles via chemistry. So I think that we should consider, if we want to get rid of grams, we need to get to moles. And then after moles, we then need to consider how to get to a number. Now, by the way, let's think about each of these separately, and let's see if we can put in the values. So this should be rho, and that's the rho of copper. By the way, this is copper. I can put the subscript Cu. So rho Cu. And then this right here is a conversion factor. So we know that 1 meter cubed, we know that there's 100 centimeters in a meter. but it's a cubic centimeter, so we must cube this relationship, okay? Now, often things are not expressed in moles per grams, but I think that we can express that as 1 over grams per mole by unit analysis. And grams per mole, via chemistry and looking at specific elements, grams per mole is exactly the atomic weight, or the atomic mass, really, of an element. And we can say that the atomic mass of copper is about 63.546. So 63.546. Now, I wouldn't necessarily know that unless I had got this information from the periodic table. And then finally, number of molecules per mole. That's a very famous number. In fact, that's exactly Avogadro's number. Okay? So then we can start to multiply all this out. So we should get, let's see, 8.95 grams per centimeter cubed times, and then 100 to the third is 10 to the sixth centimeters cubed over 1 meter cubed times 1 over 63.546 grams per mole times Avogadro's number, which is approximately 6.02 times 10 to the 23rd. And the units there are number per mole. Okay, so let's go ahead and work this out. So this calculation should be C. So, and let's make a bit of a stack out of this. So I'll go alpha F1, and I'll do a stack, and I'll do 8.95 times 10 raised to the 6th power, and then times 6.02 times 10 to the, there we go, times 10 to the 23rd, and that all divided by 63.546. Okay, so let's write this number down. This is approximately, okay, over here, 8.47 times 10 to the 28th, and that's going to be units of number per meter cubed. Okay, so number per meter cubed. So with this number in mind, this is the exact conduction electron density. Notice that this number, I showed you how to calculate it, but often these are given for you in tables. So notice that the conduction electron density is given to you in certain tables in certain textbooks, but I wanted to show you where it comes from. Okay? All right. So, again, I showed you how to calculate it. So now, let's actually calculate the drift velocity, since we know the number conduction electron density. Okay? So we'll go on to the next page, and we'll solve this equation. So in fact, I'll grab this equation, okay, here, and bring this over to the next page. Okay, fine. And let's go ahead and solve this equation for the drift velocity. So the drift velocity, Vd, should equal to the electric current for the numerator, that's I, divided by the number electron density. And by the way, part of the reason I'm doing a bit of a balloon n is because I don't want you to confuse this with an integer, nor is it number of moles, nor is it number of molecules, nor is it the number of a harmonic. Anyway, simple overusage, even in physics 2 itself, times the magnitude of a fundamental charge times the cross-sectional area of this wire. So let's substitute in all the numbers. So the electric current, I believe, on the previous page was 10.0 amperes. The number electron density we calculated to be 8.47 times 10 to the 28th. You could also just use 8.5 times 10 to the 28th. So let's just do that. 8.5 times 10 to the 28th. And remember, that's number per meter cubed times fundamental charge 1.60 times 10 to the minus 19th coulombs, and then times the cross-sectional area, which was also given on the previous page as 3.31 times 10 to the minus 6th meters squared. So 3.31 times 10 to the minus 6th meters squared for the cross-sectional area. Okay, and just to make this look a little nicer, let me move this over. Okay. Alright, so let's go ahead and get this value for the drift velocity, Vd. Okay, so let's bring up our calculator and we'll clear. Well, let me actually just move this over. Okay, so we should have, let's go alpha stack. Okay, so let's do 10 divided by, let's see, 8.5 times 10 to the 28th power times 1.60 times 10 to the minus 19th power times 3.31 times 10 to the minus 6 power. Okay, and if we calculate all that, we should get this value. So we'll write this down. It's about 2.22 times 10 to the minus 4th meters per second. Now that's the correct answer in SI units, but to give you a more realistic sense about how large these typical drift velocities are in real metals, 10 to the minus 3 is the same thing as taking a meter to a millimeter. So then 10 to the minus 4, this would be approximately 0.222 millimeters per second. So imagine this. Every 10 seconds, an electron only moves about 2 millimeters. That's extremely slow. Now you may ask, are the electrons moving in terms of their speed extremely slow? Well, no. That's because they're kind of bouncing around almost like an ideal gas, depending upon the temperature and so on. But their net movement in the direction of the electric field. Now, by the way, we know electrons actually move in the opposite direction of the electric field. We usually think of positive charges moving in the direction of conventional current. But in any case, if positive charges move in the direction of conventional current, they only move a few, not even millimeters a second a lot of times. That is very, very, very slow. So drift velocities in practice are usually very, very small. Okay? So that ends this problem. Thank you very much for your attention. Please smash that like button if you enjoyed this content, and subscribe to the channel to please grow the channel. Please share this video with people in your sphere of influence. Thank you for watching, and I will see you in the next video.